Welcome to Grade 12 Artificial Intelligence. In this lesson, we'll look inside a large language model. We'll see how text becomes tokens, how the transformer turns those tokens into predictions, and how performance improves as we scale the model up. By the end, you'll understand the architecture behind systems like the assistants you already use every day. Here is our plan for the lesson. We'll start by turning words into tokens. Then we'll step inside the transformer and meet self-attention. We'll see how the next token prediction objective trains the model and how its loss falls as a power law when we scale. We'll discuss emergent abilities with care and finish with how we adapt and shrink models for real-world use. A language model does not read letters or whole words the way we do. First, a tokenizer breaks the text into small pieces called tokens. A common English word like the often becomes a single token, while a rare or long word is split into several pieces. Each token is then mapped to an integer, an identity number the model can work with. A Kinyarwanda word, such as umugore, may split into a few subword tokens because the model learned its pieces from data. This matters in practice. The number of tokens decides how much you pay and how much text fits in the model's context. Once text is tokens, we can feed it into the transformer. Modern language models are built on an architecture called the transformer, introduced in 2017. Follow the flow upward. The tokens enter at the bottom. Each token is turned into an embedding, a list of numbers that captures its meaning. Then comes the heart of the model, self-attention. Self-attention lets every token look at every other token and decide which ones matter for its meaning here. After attention, a feed-forward step transforms each position on its own. This pair, self-attention then feed-forward, is one layer, and the model stacks many such layers, one on top of another. At the very top, the model outputs probabilities for the next token. Now, how does it learn to make those predictions well? Before a model is useful, it goes through pre-training. The idea is beautifully simple. The model reads enormous amounts of text, one token at a time. At every position, it must predict the next token. Given the words Lake Kivu is in, a good model should predict Rwanda. We then compare its prediction to the true next token and measure the error with a number called the loss. The loss is high when the model is wrong and low when it is confident and correct. The model adjusts its weights to lower that loss and repeats this billions of times. This single objective, next token prediction, is what teaches it grammar, facts, and patterns of reasoning. Naturally, this raises a question: what happens as we make the model bigger? Researchers studied what happens to the loss as we scale the model up. They found a striking regular pattern. As we give the model more compute, more data, and more parameters, the loss falls as a power law. On these axes, both scales are logarithmic, and a power law appears as a straight downward line. This means improvement is smooth and, within a wide range, predictable. We can estimate how much better a larger model will be before we train it. But the line does not fall forever. There is a floor, an irreducible loss set by the natural uncertainty in language itself. Later work, the chinchilla study, refined this. For a fixed compute budget, data and model size should grow together for the best result. Scaling reliably lowers the loss, yet something more surprising also appears. As models grow, some abilities seem to appear quite suddenly. A small model fails a task completely, and then, past a certain size, a larger model can do it. Multi-step arithmetic, step-by-step reasoning, and translation are common examples. These abilities often improve when we prompt the model to think step by step. Here we must be careful and honest. Researchers debate how sharp this emergence really is, because how we measure a task can change whether the jump looks sudden or smooth. And scale enables new behavior. It does not guarantee the answer is correct. A large model can still be confidently wrong. So the practical question becomes, how do we put these models to work? A pre-trained model knows a great deal, but rarely your exact task. There are two broad ways to adapt it. The first changes nothing inside the model. With prompting, you simply instruct the model clearly in the input. With retrieval augmented generation, often shortened to RAG, you first retrieve relevant documents and place them in the model's context so it can read the facts it needs. This is fast, cheap, and ideal for fresh or private information. The second way is fine-tuning. Here you update the model's own weights by training it on examples of your task. It costs more and changes the model itself, but it is best when you need a fixed style or a specialized skill. Once a model works well, we still want it to run efficiently. A model with billions of parameters is powerful but heavy. Two techniques make these models practical to run. The first is quantization. We store each weight using fewer bits, moving, for example, from 16 bits down to 8 or even 4. This shrinks memory and speeds up inference, usually at only a small cost in accuracy. The second is distillation. A small student model is trained to imitate a large teacher model. The student keeps much of the teacher's skill at a fraction of the size. Together, these let capable models run on a phone or on low-power devices far from a data center. Now let's see where all of this matters in the real world. These ideas already shape tools people use. In Rwanda, language models power Kinyarwanda assistance and translation, helping technology meet people in their own language. In education, a tutor can explain a hard idea in the learner's mother tongue. Across the United Kingdom and Europe, a single multilingual model can support dozens of languages at once. In United States enterprises, assistants use retrieval to search a company's own documents before answering, and quantized distilled models now run directly on phones, working even with no internet connection. One architecture, scaled and adapted, serves many very different communities. Before we review, let's clear up some common misconceptions. First, a model predicts the next token from patterns. It is not looking up whole sentences stored in a database. Second, scaling laws are empirical trends measured over a range. They are not exact guarantees that hold forever. Third, an emergent ability does not mean the model truly understands the way a person does. Fourth, more scale does not make a model always correct. Even the largest model can be confidently wrong. And finally, keep the methods apart. Fine-tuning changes the model's weights, while prompting and retrieval do not. Hold these distinctions and your understanding will stay sound. Let's gather today's key ideas. Text is first split into tokens, each mapped to an integer. The transformer stacks self-attention and feed-forward layers to process those tokens. Pre-training works by predicting the next token and lowering the loss. As we scale compute, data, and parameters, the loss falls as a power law. Some abilities appear more sharply with scale, though we read such claims carefully. And we adapt models with prompting, retrieval, and fine-tuning, then shrink them with quantization and distillation. Now, let's check your understanding with 3 quick questions. Here is the first question. During pre-training, what is the model trained to do at each position in the text? At every position, the model predicts the next token and adjusts its weights to lower the loss when it is wrong. That single objective, next token prediction, drives all of pre-training. Question 2. On log-log axis, the test loss against compute appears as a straight, downward line. What does that shape tell us? A straight line on logarithmic axis is the signature of a power law. So the loss falls as a power law as compute grows, which makes the improvement smooth and, within a range, predictable. Last question, and it combines several ideas. You need a model to answer using your company's latest internal documents, but you cannot retrain it. Which approach fits best? Fine-tuning would change the weights and needs training, so it does not fit here. Retrieval augmented generation is the answer. You retrieve the relevant documents and place them in the model's context with no retraining at all. It is ideal for fresh or private facts. Wonderful work. You now know how a large language model is built, from tokens through the transformer and self-attention to next token prediction. You can read a scaling law, weigh claims about emergence, and choose between prompting, retrieval, and fine-tuning. Take a moment to revisit the diagrams on your own. In the next module, we'll explore how these models are trained safely, aligned with human values, and used responsibly. I'll see you there.